All right. Hey guys, I'm going to go ahead and write up a sort of a warm-up exercise. Yeah. Well, we'll see. We'll see if how many more people join. If it's just like one or two people, I might kind of like convert this into more of an office hours type thing. I'm not sure. We'll see. But anyway, so here we go. Here's a little exercise. So suppose f is a real valued continuous function on R, and f of b is less than 0 for some a, b in R. Show there exists an x between a and b such that f of x equals 0. So yeah, let's take, yeah, we'll say like 513 or so. Yeah. All right, great. So it looks like there are quite a few people here actually, which is good. Hopefully this didn't take too long. It's essentially just an application of the intermediate value theorem. So basically what you can say is, if f of a, f of b is less than 0, either f of a is greater than 0 and f of b is less than 0, or f of a is less than 0 and f of b is greater than 0. We can just assume pretty much without loss of generality that let's say f of a is less than 0 and f of b is greater than 0. Then I mean, actually we don't even have to, never mind, just forget it. Either way, right? So in either case, zero is between f of a and f of b, right? And clearly a can't equal b, obviously, because otherwise, well, this would be impossible, right? So so the intermediate value theorem tells us that there exists some x between a and b such that f of x equals 0, right? That's pretty much it. So it's literally just the intermediate value theorem after you kind of like unpack this assumption that f of a times f of b is less than 0. Okay? Any questions about that? Okay, hold on. Actually, let me, since there are more people, let me bring up the participant list. Where is it? Oh, weird. Oh yeah, here we go. Great, yeah. So if you want to like, if you want to ask a question at any point, you can do the like hand raising thing, and I should be able to see it. All right. So anyway, okay. Well, so I have several more exercises that I think are pretty good. I mean, they're things that I sort of picked out from the section of the book, because there are like quite a few good exercises for this section, I think, and so I picked some that I didn't put on the homeworks that I think are like pretty healthy exercises. Before we get into that, though, I'm also happy to take any generic questions you might have about the material so far, especially the most recent material. And again, apologies for I don't know what happened. I just forgot to like actually publish the videos last night, even though I did make the playlist public. I think maybe somewhere in my mind, I thought maybe that would make all the videos public or something. I'm not sure. But anyway, yeah, so apologies about that. I know you haven't had as much time to sit with this recent material as with the other ones. But yeah. All right, so if there are no questions about that, then I'll go ahead and give you guys another exercise. Let's see. Which one will be good? Here's another relatively quick one. It's slightly more complicated than the last one, but I think, actually, do we want to do this? Now we'll skip it. All right, let's do this. Let's do this one. So let S be a subset of R, and suppose there exists a sequence xn in S converging to a number x naught not in S. Show there exists an unbounded continuous function on S. Okay. So yeah, I'm gonna go ahead and make like 2 little rooms here for you guys to work together if you want. Yeah. Okay. Sure. So let's say we'll resume at like 5:27, 28. Say 5:27. I think it shouldn't take too long.
I'm sorry, Max. Can you invite me again to the breakout room?
Oh yeah, sure. Let's see.
Okay.
Oh, okay. All right, so was anyone able to come up with a description of some unbounded continuous function on S? All right, no worries. So here's a simple answer. Okay, so I think one of the pitfalls with this problem is that you might get trapped into like thinking about how to build a function, a continuous function that like hits like a higher and higher value at each like xn basically. Like you want, because right, the idea is that the fact that xn converges to a number outside of S means that you can make the values of your function get bigger and bigger for each xn, and it won't cause a problem because you don't have to define the value of f at x naught specifically, right? So like I think when I at least for like a few seconds when I first looked at this problem, in my head I was just visualizing like making these kind of like bump functions, I guess, that get like taller and taller and taller, and each one is like centered at xn or something. But there's actually like a much easier way of doing this, which is just to make an unbounded continuous function on all of R without the point x naught, and then that approaches infinity near x naught, right? Or like plus or minus infinity, and then just restrict that to the set S basically. So so solution would be to take f of x equals 1 over x minus x naught, right? Then f is continuous on R minus the point x naught. So f is continuous on S, right? Since S doesn't, S is a subset, right, of this set here. So so f is continuous on S, and then f is unbounded on S because well, okay, f of xn is unbounded. Okay, and this is because if how to put this? I think you can say if xn minus x naught is less than epsilon, I believe the absolute value of f of xn, I think, is just bigger than 1 over epsilon. I think you can show this. Okay. So yeah. Any questions about that? So like by taking smaller and smaller epsilons, right, you can find points xn where absolute value of f of xn is bigger and bigger.
This seems like a pretty
No, go ahead.
like simple answer. I just mean like, when are you allowed to kind of just like make this function? That's, I don't know if you understand my question. Or
Yeah, I'm not
okay,
totally sure I understand.
for some other like exercises or problems, like it's there's like a lot of things that you need to do to show how you can like construct a certain sequence, it seems like to me. But here you can just say what it is.
Yeah, I mean, yeah, I'm not, it's a hard question to answer. It's just, I mean, yeah, it's just that in this case, you know, I guess we're lucky that there is a simple description, I guess. I don't know. I'm not really sure what else to say.
Okay.
I mean, the reason this function works is because, you know, the only point that's missing from its domain is a point that we know is not in S, I guess, right? So, you know, the fact that it is defined and continuous for all other values of X is what makes it so that you know, it'll automatically be continuous on S. And then we know that it just approaches infinity or negative infinity close to X naught. So since we know that these points xn are getting close to x naught, and the points xn are all in S, then the values of f at those points has to grow unboundedly.
Right. Okay.
Yeah. Mm-hmm. I do want to use this as an opportunity to talk a little bit more about some of these like weird subtleties of like continuity of functions on various like sets and stuff. So I think I'm gonna also include, I'm planning to make like another video that's kind of like about functions, and it's gonna include a lot of stuff about like, you know, images of sets under functions, or like inverse images of sets under functions, and then also like restricting the domain of functions. I think I kind of mentioned restricting the domain in the first video, but I didn't really talk very much about it. So like if f is a function, right, with domain, let's just say, you know, this is the symbol we use, at least in this class, for the domain of f, right? And it's some set. And here I don't even want to like assume that the domain is a subset of the real numbers, although, you know, obviously for our applications, it almost always is a subset of the real numbers. But in this case, just consider it like an abstract set, basically, because all of these definitions just work for like arbitrary functions on arbitrary sets mapping into arbitrary other sets. So if f is a function with this domain, then, so if S is any subset of the domain of f, the restriction of f to S is another function which we symbolize by f. So there's like a vertical line, and then like S is like a subscript. Sometimes people just write S like normally and not as a subscript. You know, conventions vary, I guess. But if you see like f with a vertical line like this, and then a set after that, that's the restriction. This is technically a new function, right? And basically, the domain of the restriction, is just S. Okay, so basically all the restriction is it's just like you take f and then you just throw out some of the values in the domain. You know, so f of f restriction to S of x equals f of x for x in S. So the values are the same, right? The values agree with the original values of the function f, but in this case, it's like f restricted to S is just not defined for any of the points in the domain of f that weren't in S to begin with, basically. So so like as an example of this, right? If f of x, and this is it, I mean, yeah, I'm getting to something, you'll see. But so if f of x is x squared, and like S is, you know, 0, 1, union, like 2, union 3, 4, I don't know, something like that, right? So then you get like, so here's the overall, oops, okay, hold on. Okay, there's like the overall function, and then if this is like 0, 1, 2, 3, 4, I don't know. Then like we'll have this, and then like that, and then like this, right? That becomes the, so this is like f of x. But then if we want to look at the graph of the restriction, that's the graph of the restriction, right? So then this is the graph of f restricted to s, and f restricted to s is just not defined in like these regions, right? Any of the regions outside of s itself, the restriction of f is just not defined there. So a really weird thing about this, and this is kind of what I was trying to allude to with the whole like example thing, or the lecture question about like f whose a function f whose domain is like the natural numbers, is like if f is continuous, then f restricted to s is continuous, right? And when we just say continuous, we mean like on the whole domain. So if f is continuous on its whole domain, then the restriction is continuous on the whole domain of the restriction, right? Which is just s. But if f restricted to s is continuous, f might not even be continuous at a point in S. Okay. So like, even if the restriction is actually a continuous function in the sense that the restriction is continuous, it's still possible that there are points in S where the original function f is not continuous. Okay. As an example of this, like if you look at this restriction here, and then we pretend that it was actually the restriction of a different function. Okay. Like if you look at this function here, this function is continuous, right? I mean, it's continuous on these intervals, kind of like obviously. It's continuous at this point where x equals 2, just because like this point is isolated, right? So whenever there's like an isolated point in the domain of the function, it doesn't matter what the value of the function is there. It's automatically continuous because that point is isolated. So there are no other points nearby where f is defined and you can have like jumping, the value like jump around basically, okay? So f is automatically, like a function like this is automatically continuous here. But if it came by restricting, instead of restricting the function f of x equals x squared, what if the original function was defined with like 0 in these intervals, right? Between like 1 and 2 and between 2 and 3, if the original function was just 0, then the original function would not have been continuous at this point, right? So, but even though the restriction of the function to this set is actually continuous on all of the set S, right? So it's like a very counterintuitive thing. And the reason I bring this up is because like in this case, we're really using the fact that like f of x here is like continuous on all of R to say that the restriction of f to S is continuous. But like, I don't know, you can't really go backwards, I guess. So yeah, well, whatever. Yeah. But I do think that this is like an important nuance to be aware of. Okay. I don't know. It's not super important for this specific problem, but yeah, you do want to get used to thinking about like restrictions, I guess, is kind of, because I think the book, I don't know, it kind of annoys me. The book is like purposefully vague about this kind of thing because they say stuff like, when they say something like where was it? Let's see. Oh yeah, show that there's a continuous function on S. Like when they say stuff like on S, it's kind of unclear whether they're talking about like a function whose domain is equal to S that's continuous, or a function with a larger domain that is continuous at every point in S, basically. Those are like subtly different concepts. Although I think they really just mean the former, that like if you restrict F to S, it's continuous, I guess, is all that they really care about in this problem. So basically, i.e. f such that f restricted to s is continuous, which is weaker than what I was saying. Like if you have to define f for like all of R, which is what we ended up doing, but you could define f for like all of R and then make it continuous on all of R, and then obviously the restriction will be continuous. But you could have like defined it on S specifically, and then maybe it isn't actually the restriction of a continuous function on R or something. I don't know. Anyway, yeah. Do you have any questions about that? I know it's like kind of confusing, but it's just the way the definitions work. The good news is that, and I kind of like, this comes back up with uniform continuity too, which is that's the topic of like the next lecture. And I kind of like tried to talk more about this, but basically, as I say in that video too, like the good news is that usually, we're mostly dealing with like, whenever we're dealing with like restrictions, we're usually dealing with restrictions of a function to like an interval. And so if you are looking at an interval, you can say that like, at least for the points in the interior of the interval, if the restriction of f to an interval is continuous, then the original f had to have been continuous at least at all the points in the interior. So I'll explain that like in a video that I make too. I definitely think maybe this weekend I'm gonna make this like supplementary video or something that explains this. All right, so let's do one more problem. Let's see. I think. I kind of like. All right, let's try this one. I'm kind of torn between two problems. All right, I think this will be good. So let f of x equals sine of 1 over x. Oops, whoa. Oh, there we go. For x not equal to 0, and set f of 0 equals 0. So we're defining f for all, on all of R, okay? So, right, so then f is discontinuous, right, at x equals 0. This is something that I think I showed as like an example. I think it's also actually a homework problem, but I mean, whatever. I think I showed this as an example in lecture, that this function is discontinuous at x equals 0. And in fact, there's no value you can use to define f at 0 and make it continuous. That's just impossible. But yeah, so show that. So well, we know it's discontinuous, but show that f has the intermediate value property on R, i.e. if A is less than B in R and Y is between f of A and f of B, you know, strictly, then there exists an x in AB such that f of x equals y. Okay. So the fact that f is discontinuous here means you can't just like directly invoke the intermediate value theorem. Like, it's not a one-line proof. Okay. You have to be a little bit more careful. But yeah, the point of this is that it's an example of a function that has the intermediate value property on the entire real line and still fails to be continuous, basically. So this is kind of about like the whole like converse thing, as I was saying in lecture, where it's like you can make a partial converse of the intermediate value theorem, where you can say like, you know, if f is increasing and it has the intermediate value property, then it's continuous. But if you just say that f has the intermediate value property, that does not mean that it's continuous, because this counterexample shows that there are discontinuous functions that still have the intermediate value property. Okay, anyway, so I'll go ahead and open the rooms again. And let's say we'll resume at like 555. All right. All right, so this hopefully wasn't too bad. There is like a relatively concise solution here. So, okay, what do we want to do? All right, let's say let a, let's say, yeah, a less than b, right? So we want to show, and or let's yeah, let y be between f of a and f of b, right? Okay, so then there are basically like some cases we can easily take care of. So like, case one, either a is less than b less than 0, or 0 less than a less than b. So if they're like both, if a and b are both on like one side, right, then the intermediate value theorem for like either in this case, if a less than b less than 0, then like f restricted to like -infinity 0, or f restricted to 0 infinity gives the desired x such that f of x equals y. Because if you restrict, right, if you restrict to one of these like open intervals like this, then the restriction is continuous. Okay. Does that make sense? Hold on. Okay, yeah. So basically, yeah, the fact that like the original f, I mean, maybe instead of saying it in terms of restrictions, what you can say is like the original f is continuous at every point in either of these two like open intervals. Okay, so so you can just like use the intermediate value theorem for these cases, and everything's fine. So then we just have to consider the case where like, okay, case two, let's say, a is less than or equal to 0, less than b, or a less than 0, less than or equal to b, I believe, are the only two other possibilities we have to consider. And let's say without loss of generality, say a is less than or equal to 0, less than b. Okay, like the other case is like just a mirror, kind of a mirror image of this. Okay, so then the key is that f achieves all values in -1, 1 on, even just like 0b is enough, right? So clearly we can find, okay, so why is this? Let's okay, let's actually justify this, right? Why? We can, basically it's because like there's an infinite number of arches of the sine function that happen in this interval, right? Because we have like sine of 1 over x, right? So we can take, let's say like, what is it? We want x to be 1 over, yeah, right, okay. So take n such that like 1 over 2 pi n is less than b, then 1 over 2 pi n plus 1 is less than b, right? And or rather, actually, maybe it would be better to say, instead of 2 pi n, let's say like 2 pi n like plus pi over 2, right? And then here, what we can say is we'll have like 2 pi n plus 3 pi over 2. And f of, if we call this like, I don't know, A1, I don't know, and then call this like B1 or something. I hate that notation, but whatever. F of A1 is like 1, and f of B1 is -1. So, you know, there exists an x in like A1, B1, such that f of x equals y, where y, remember, y is like the original target value that we're trying to hit, because automatically -1 is less than or equal to y less than or equal to 1, right? So, oh, I guess this is if, right? So if y equals plus or minus 1, choose x equals A1 or B1 accordingly. So if y is not plus or minus 1, then it's like strictly between, right? So then, I mean, I guess actually the original assumption that y is, well, we didn't say strictly here. It doesn't matter. It really doesn't matter. Okay, anyway, so yeah, if y is strictly between plus or minus 1, then we can just find, using the intermediate value theorem, by the intermediate value theorem, for, you know, f restricted to, let's say, 0, infinity, or whatever, right? So that's basically it, right? Because if x is in A1, B1, that implies that x is in AB, because B1 is less than or equal to B, and A1 is greater than or equal to 0, which is greater than or equal to A. So, yeah. Or well, actually, no. B1 is like strictly less than B, and A1 is strictly greater than, yeah, greater than 0. Oh, I guess the labeling here is actually like flipped, I think. Yeah, because this one's smaller, so this should be B1, and this should be A1. Okay, sorry. We got a little bit gnarly, but not too bad. Any questions?
I'm kind of confused about that last thing you wrote, the last implication.
This here?
Yeah.
Yeah, because A1 and B1 here, let me just like draw a diagram. So here. So we have this. So the point is like, okay, we're assuming that A is over here and then B is over here. And A could possibly be 0. It doesn't really matter. All we did was we found like, here's like B1, which is like 1 over 2 pi n plus pi over 2 for some large n, right? And then A1, well, this is A1, which is 1 over 2 pi n plus 3 pi over 2, right? And so we know that the value of the function, oh, dang. Okay, I'm going to erase these arrows for now. Okay, we know that the value of the function here at A1 is -1. So let's say that's there. And then at B1, it's +1, right? So that there's like a piece of the function that looks kind of like this, all right? So this is A1, and then this is B1, right? So then what we did was we found, you know, let's say y is like here or something, right? We found x inside this interval A1, B1, right? But A1, B1, by the way we by the way we constructed it, because B1 is smaller than B and A1 is bigger than 0, right, which is bigger than A. So by the way we constructed this interval, it's inside of the larger interval AB, right? So because X is in this small interval here, it also has to be in the big interval. That's what this is saying.
Okay, that was helpful. Thank you.
Yeah. Yeah, sorry. I every once in a while, I don't know, I try to like have this like golden rule of just like always sketch things whenever possible, and I just sometimes I get lazy and I just don't do it. But yeah, so this is sort of like what it looks like. And then, you know, of course, the function is doing other stuff. The waves get further and further apart out here, and then they get like closer and closer and closer together over here. And then there's sort of this crazy whatever insanity. And then, you know, who knows, right? But anyway, so we found like one specific like you know, two halves of arches like this, that where it's like all the values happen, they have to happen somewhere. So yeah. Any other questions? All righty. Yeah, so I think the next lecture should be finished earlier than the last one was. So hopefully that's some, you know, consolation. I'm getting like back aligned with the schedule that I originally tried to maintain. So hopefully from here on things are a little bit smoother. Yeah, so hopefully I'll see you guys tomorrow, and we'll talk about uniform continuity.
Thank you.
Mm-hmm.
Thank you.